Hello, everyone, and welcome back to the Mid-Atlantic Micro Nano Alliance's virtual seminar series. I'm MAMNA co-president Ryan Sokol, and today I'm joined by our MAMNA treasurer, Oliver Barham, who will be our virtual host for today. Oliver, who do we have today?
Thank you, Ryan. Hi, everyone. As Ryan mentioned, I'm MAMNA treasurer, Oliver Barham, and I'm filling in for our president, Heidi Leonard, today, in co-hosting duties, Ryan. So I have the pleasure of introducing for this talk one of my coworkers. We work together about an hour south of DC at Naval Surface Warfare Center, Indian Head Division. This is a government R&D lab about an hour south of DC. We work on energy and energetics related concepts. And in this talk, well, before we get to the talk, Mohammed will do that, but Mohammed's background is an electrical engineer. He's done circuit design and microfabrication design. At Indian Head, he's our lead MEMS fabrication designer and engineer. He fabricates all of our MEMS devices, and he has a background additionally in wide bandgap semiconductors. So that microfabrication experience is going to tie right into this talk today. So Mohammed, take it away.
Okay, thank you, Oliver, for the introduction. Hello, everyone. My name is Mohammed Khan, and today I'm going to present on non-chemical high-temperature betavoltaic power source. Before I begin, I would like to acknowledge the people who helped me with this research. First of all, my PhD advisor at University of Maryland, Professor Aegis Iliadis, Mark Litz, Ken Jones and his group at the U.S. Army Research Lab, Oliver Barham, who's my colleague and mentor at NSWC Indian Head, and Tom Adams from NSWC Crane and Purdue University. So I want to start off by showing you this chart here. It shows the progress of iPhone over the years. As you can see here, iPhone 6, which came out in 2014, its performance in terms of processing speed and graphics increased by 50 times, whereas its battery capacity only increased by 1.3 times. So energy density determines the battery capacity, which means how much energy can we pack on a given footprint or volume of the device. If you look at the next chart here, it shows the energy densities of different batteries. iPhone uses lithium-ion batteries, and you can see here that lithium-ion batteries have low energy density compared to beta sources, which are shown at the top in red. So beta sources have magnitudes of higher energy density, which means given the same footprint, we will have much more energy or increased battery capacity compared to low energy density chemical batteries or lithium-ion batteries. So beta sources also have really long lifetimes. We're talking about a power source that can last you 10 to 100 years, and they have much wider operational temperature range than chemical batteries. So what is a beta source? A beta source is basically an unstable nucleus of an atom that wants to stabilize itself by splitting into an electron and a proton. The proton stays with the neutron, whereas electron makes its way out of the nucleus carrying some energy. And that emitted electron is basically the beta particle. With nuclear energy or radiation, safety is a big concern. As you can see here, beta particles can easily be stopped by your skin. And there are beta sources used around us, most commonly found in exit signs or watches that glow in the dark. They contain tritium beta source. So if we make a betavoltaic power source out of tritium, same regulations will apply as an exit sign carrying tritium. So now, what is a betavoltaic power source? So betavoltaic power source is a device that converts the emitted electron and converts it into electrical energy. So it is a constant power generation device. It is not a battery. It doesn't store charge. And its working principle is similar to solar cells. In solar cells, we have photons from the sunlight generating electron-hole pairs, whereas in betavoltaic power source, we have beta particles generating power. So with solar cells, we're always dependent on the sunlight. When there is no sunlight, there will be no photons and we don't get any power. But in case of betavoltaics, we have a beta source which is coupled right on top of the semiconductor junction. meaning that we always have a source of beta particles, generating electron hole pairs and power. So this power source is not dependent on anything. It will work everywhere underwater at much higher and lower temperatures as well. Its main drawback is the output power. It's typically in the tens of microwatts per centimeter square, and we are trying to increase that. So betavoltaic devices are ideal for devices that require small amount of power over long periods of time, such as sensors placed in remote areas where change of batteries can be burdensome or dangerous, or implantable medical devices, such as a cardiac pacemaker. So actually in 1980s, approximately 150 patients were implanted with cardiac pacemakers powered by beta sources. But then lithium-ion batteries came along and they were so much cheaper that they took over the market. So if you look at figure 6, that is a wearable glass sensor built in-house at Indian Head. This sensor project was funded by Office of Naval Research, and they wanted to field this sensor by putting it on the helmets of the troops to collect blast events that are capable of causing mild traumatic brain injury. So the goal of this project was to make this sensor package as small as possible. As you can see here, our MEMS sensor itself is very small. It's only 36 millimeters square, but the battery size is much larger. So because of the battery size, we were not able to make this whole sensor package smaller. But if you use a betavoltaic power source, we can significantly reduce the package size. These are the power levels required for this sensor package, and we can easily achieve these power levels with a betavoltaic power source. So in some applications where a betavoltaic power source cannot directly provide power, it can be used with lithium-ion batteries. So in case of a tiny drone, it is used for surveillance purposes, and its current flight time is approximately 30 minutes. So if we use a beta source with a lithium-ion battery, we will put them together, and a beta source, which is a constant power source, gives you power 24/7. It can charge the lithium-ion battery. Then you can have your drone, fly, take a break to recharge, and then continue mission without coming home, without coming to the station. As you can see here, this tiny drone has like bird-like claws for perching. So design consideration. So when we're looking for a semiconductor, we are looking for a material which will give us higher efficiency and which will be resistant to high energy beta particles. So if you look at this figure 8 here, it shows the efficiency of a betavoltaic device as a function of energy band gap. And efficiency increases as the band gap increases of the material. So if you look at the solar cells, photons have different energy levels. We're not worried about photons damaging the atomic lattice structure of the crystal. But with betavoltaic power sources, if we use a narrow bandgap semiconductor, it damages the atomic lattice structure of the crystal, which degrades the performance of the device as time moves on. So basically, a wider bandgap semiconductor gives us a more efficient device, and it gives us a device that doesn't easily get damaged by the beta radiations. So figure 9 here shows basically what happens when a beta particle interacts with the semiconductor junction. As you can see here, beta particle generates electron hole pairs throughout the junction. The electron hole pairs that are created within this collection area, they get collected and contribute to the current or to the output power, whereas electron hole pairs that are created outside this region, they don't get collected. They simply recombine and don't contribute anything to the output power. So we fabricated betavoltaic devices on gallium nitride semiconductor. Our GaN wafer was grown using MOCVD method on top of a sapphire substrate. Figure 10 here shows the side view of the wafer with the doping levels and layer thicknesses. Then we fabricated our devices using standard photolithography, etching, and metal deposition. You can see here on figure 10 to the right. And then we wire bonded and packaged our device into a chip carrier. Figure 11 shows fabrication process flow. Then we characterize our devices, which I'll talk about next. So first, we characterize the semiconductor junction itself. So we did dark IV measurements, which means we tested our semiconductor junction without illuminating it with photons or betas. And we saw good diode behavior. So we saw good rectification as shown in the green here. So then since the working principle of a solar cell is similar to betavoltaic device, we wanted to see if our device behaves as a solar cell. So we tested it under a light source. And we clearly saw a photo response as the IV curve dropped down to the fourth quadrant, indicating that the power was generated. So the wavelength for the light source was 310 nanometers, which equals to about 4 eV. So the output power was 8 nanowatts. So to get output power, we simply multiply voltage times current, so we get 8. So since we did not have access to beta sources in our lab, we tested our devices under an electron beam system. So electron beam system emitted electrons at different energies, and we performed a sweep from 1 keV up to 16 keV. And we, so this is the output that we got. As you can see here, the IV curve dropped further and further into the fourth quadrant as the input energy of the E-beam was increased. So we got an output power of 70 nanowatts at the energy equivalent for tritium, which is about 5.6. And we got an output power of 640 nanowatts at the energy equivalent of nickel 63. So which is, so the energy of nickel 63 is 17 keV, or electron beam system can go only up to 16 keV. So we extrapolated to get the output power of nickel 63 at 17 keV. So figure 15 here shows the beta's penetration depth in GaN. As you can see here, nickel 63 has 17 keV energy, and it penetrates deep into the N layer. And so this middle layer is the depletion region. So as it penetrates further into the N layer, it creates electron hole pairs that are not collected and contribute to the output power. So basically, these electron hole pairs, they simply recombine and don't contribute to the output power. So since GaN is a direct bandgap semiconductor, when recombination of electron and hole generates a photon, so which is shown in this LED video here. I will say it. As you can see here, we have a clear LED behavior. So we did find a major design issue in our with our devices. So we were trying to, so when we did the dark IV in the log scale, we noticed an unexpected behavior. It's shown here. Like we saw a second bump here, which should not have been there. So this indicates that we have two junctions instead of one. So when we design our devices, we wanted our devices to look like this. We wanted one depletion region which would extend from P layer all the way down to N layer. But we ended up getting these two depletion regions, W1 and W2. So we had some undepleted region in between the two depletion regions, so which reduced the collection efficiency of our device. So we did our calculations again, and we figured that an I layer, which is intrinsic layer, the width of 500 nanometers will give us a depletion region which will extend from P layer all the way down to N layer. So in conclusion, we made betavoltaic devices, gallium nitride film grown on top of sapphire substrate, and we got output power for nickel 63, 6.4 microwatts per centimeter square with an overall efficiency of 4%. For tritium, we got an output power of 0.7 microwatts per centimeter square with an overall efficiency of 1.2%. One big concern with betavoltaics is that high energy beta particles can damage the atomic lattice structure of the semiconductor. So we did the dark IV after the EV measurements to see if there was any damage. We did not notice any damage. So our devices behave similarly before and after the EV measurements. So in the future, we want to fabricate our devices on GaN, which will be grown on top of the GaN substrate. There will be no lattice mismatch as in the previous case, and there will be less dislocations. And we want to optimize our intrinsic layer to 500 nanometers, which I talked about in the previous slide. And then we designed a new mask to reduce the P contact area. So if you look at figure 17 to the left, you notice that this P contacts, they're covering about 30% of the device area. So 30% of the beta particles, they are reflected back. They're not creating electron hole pairs. So to the right is our new optimized design. And then we will look into other materials such as gallium oxide for better device performance. So these are the references for my talk, and I'll be happy to answer any questions.
Thank you very much, Mohammed. And that was a great job. That was a very cool talk, although I'm biased because of helping you with it a little bit. So we'd like to open up the internet to questions right now. And as we're saying, don't be bashful. And we're going to start taking questions live right now through your Q&A in the chat window. So the first question for you, Mohammed, comes from Zachary Ferraro. And he says, are betavoltaic devices or the packaging associated with design sensitive to thermal, vibration, or shock compared to lithium-ion batteries?
They have much more tolerance, like vibrational tolerance compared to lithium-ion batteries. So they can function at much harsher environments compared to chemical batteries.
But you haven't done any shock testing on them yet, is that right?
Yeah, we haven't done any shock testing on them yet. Yes, that is correct.
But it is something that we think, you don't see any reason why they should perform worse. You think they should be better than lithium batteries, is that right?
It is a solid state device, so everything, when it's fully packaged, it's very robust, so it should perform better than chemical batteries in terms of vibration.
Okay, very good. Okay, let's see here. We have another question from Frank Linnell. Have you measured the reverse characteristics of the diodes?
Yes, we did look at the breakdown voltage, and we had very little loss when looking at the diode performance in reverse bias. So I don't have that number here, but I think it was very little loss.
Okay, next question is from Tuan, who says, why not use alpha particles instead of beta, another type of radiation? Aren't alpha particles safer? Maybe you can go back to that first slide you had with the safety.
Yeah, alpha particles, even though they don't penetrate like through a paper, but they contain much high energy levels. Like their energy levels are like 5 mega electron volts or higher. So they can damage the semiconductor junction more easily. So that's the reason we do not use them.
Okay. And looks like Brendan Hanrahan says, what are the techniques to improve power density? So how are you going to make it more power dense in the future?
We have to use the more energy dense material. So that's why we're using beta sources. I mean, these beta sources have such high energy density that they can give you a lot of power from a very tiny material. We just have to find ways to increase their efficiency and their output power.
And are there any other tricks? So what about the design, different designs you might look at to try to increase the power density for a given radiation source?
Yeah, there are like techniques out there. We made like planar devices. Some people, they are creating trenches, that increases the surface area of the device. So that can give, higher output power. The footprint of the device will be the same, but, it will have more surface area for the electron hole pairs uh, uh, for beta particles to create electron hole pairs. So that can give you more power.
Okay, well, we're waiting for a couple more questions. I have another one that might be interesting to people. So in this work that you were doing, you didn't actually handle any of the tritium or nickel 63 yourself, right? So you did all of this work without ever having to handle the radiation sources. So it is possible to work in this area without handling the radiation directly. Is that right?
That is right. So we used so beta particles are basically electrons. So we used an e-beam system which emits like electrons at various energies. So we used them to simulate sort of like devices' behavior as betavoltaic devices.
So if someone out there is interested in maybe working in this area, but isn't sure about the radiation aspect, if they can build semiconductor devices, they could partner with someone else and put together a device, right?
That is right. Yeah. So that's why I'm collaborating with Mark Litz from U.S. Army Research Lab and Tom Adams from NSWC Crane. They have beta labs where they can test, at least with tritium, beta sources. So I'm not going to work with beta sources directly. I will fabricate betavoltaic devices, and then I will be collaborating with them to test them as betavoltaic devices. But I can test them using an electron beam system to sort of predict their behavior.
Cool. Let's see. Is there any other questions out there on the internet? That might be it. Anything else you thought of you might want to add, Mohammed?
Not really. Thank you for giving me an opportunity to share my research work. I'm going to be working on this for my PhD dissertation, and I'll be looking into improving like the efficiency of these devices, and maybe looking into gallium oxide to see, it has an ultra wide band gap to see, if we get better performance with gallium oxide.
Okay, very cool. Thank you again, Mohammed, for talking. That was great. And Ryan, any final thoughts, and who do we have next week?
So obviously a great talk. For next week, we're going to have Alexis Payne, who is a PhD student from North Carolina State University and the U.S. Army Research Laboratory, who's going to be presenting on atomic layer dielectrics on metal foams for energy storage. But for today, I just want to thank Mohammed again for a great talk, and I'll see you all next week.
Thank you so much.
Bye, everybody.
Okay, I think we